Hi, everyone. We are extremely sorry for the delay and starting the session 10 minutes later. As I mentioned, we had some technical issues connecting to the session, but hopefully everything will work well from now. So my name is Moria, and I'm the Reactor Program Manager based in Tel Aviv. And we are going to kick off the session on Explore Logistic Regression soon, and it will be presented by Brian Sletten. So before we start, I wanted to let you know the session will be recorded. I'm going to share with you the link to the YouTube channel where you can find the recording there. It will take us a few days to upload it, but you should be there by next week. We also encourage you to ask questions during the session, so please feel free to use the Q&A box on your screen, and we will take the time to answer your questions at the end of the presentation. Last thing from me is that I'm going to share with you a link to the survey that we conduct for our events, and appreciate if you can take a minute or two to provide your feedback on this event. I'm going to share as well the event code, which is 11879. I will post it in the chat box soon, so you can join the survey and complete it after the event. So that's it from my end. I'm going to pass it on to Brian now so he can kick off the session. Enjoy. Thank you.
All right, thank you very much. And I apologize about the connection issues. I had to swap everything over to another computer at the last minute. So I hope I got everything right and we're able to move on. Let me make sure here. Okay. So my name is Brian Sletten. I'm an independent software consultant. I live in Northern California, and I've been teaching people about machine learning kind of around the world for the last several years. And so it's a pleasure to be able to reach out and speak to you today. We're going to be talking specifically about building to being able to use a technique to make some predictive models. And we're going to first start by introducing you to the data set and getting you ready to go. And we're going to use Visual Studio Code for that and walk you through a Jupyter notebook. So the examples are available to you through the Microsoft Reactor GitHub repo. If you check that out and then look under the work, trying to remember exactly where it is. It's under the workshops and then Data Science 1. There is a project under there called Loan Project, and we are going to walk you through that. So I'm assuming that you've had some background and exposure to working with Jupyter notebooks and perhaps some basic Python interactions, but beyond that, I won't make too many assumptions. If you could call out if there are any questions. This other computer that I'm on is a smaller screen, so I can't see the chat and maximize at the same time. So that would be helpful if you could call out if there are any questions. I'll check in at the end. So the scenario here is that you work for some kind of company that provides data science capabilities, and one of the things that you may work on is helping people understand their likelihood or their opportunities for acquiring loans, which obviously is going to be based on what we know about the individual users. Now, there's clearly some information that is usable and some information that isn't. And when you start collecting data, there's definitely a sort of ethical requirement in terms of the guidance about which data you can use for certain things like loan qualifications. And in fact, as we say here, the Certified Analytics Professional in United States Statistics Division have codes of conduct and declarations about ethical uses of information as well. So part of the data cleanup process is about making the data prepared to be used in a machine learning capability. And part of it is also to make it so that you can make the data better, but also meet any kind of regulatory guidance as well. So we're going to look at the data that's available to us in a file that's also in the repo. So if you come to this after the session and check out the code, you should be able to run this by opening up VS Code and opening the Jupyter Notebook in the directory. So it's under the Loan project. I've selected the IPython notebook, and with VS Code's Python extension installed, it's able to execute this within the tool. Normally, you have to run Jupyter Notebook separately and get it viewed in a browser. But here we can do interactions with VS Code as well. So what you see here are a series of cells, and the cells are either documentation cells that will help us with our narrative or actual code cells. So the first part introduces the problem. You're a data scientist trying to analyze some loan-related data. And the whole purpose of machine learning is to collect some information and then try to find some patterns in there that give you some kind of predictive power. So that's what we're going to build to, is being able to predict whether applicants will be able to acquire a loan based on what we know about them. So the data dictionary that we have has existing historical data, the ID of a loan, the gender of the applicant, whether they were married or not, whether they have dependents, their graduate or undergraduate level of education, whether they're self-employed, what there is the income for the primary applicant or the income of it if there's a co-applicant on it, how big the loan was in terms of thousands of dollars, the term of the loan in terms of how many months, and then whether the credit history is established for the applicant or not, whether the property area is in an urban or a rural area, and the outcome of the loan. So there's a lot of information here. Not all of it are we able to use. So we'll see very quickly, we don't give people loans based on their gender or their marital status. So we're going to drop those fields from our training sets. But obviously the other parts of it, maybe people who have certain incomes and certain education levels will qualify for certain kinds of loans. And, again, this data set is telling us more about the likelihood of the outcome. Not necessarily, it's not going to necessarily explain why the outcome is what it was, but with some exploration, we can maybe draw some conclusions by looking through the data itself. So the process of data science is generally collecting some information, storing it, trying to understand it. If you understand it well, there may not be any real need to go into a whole machine learning activity. You could just make some presentations and explain the data that you have. But because we're dealing with data volumes that are growing very, very large, and we're pulling information from ever more sources, there's a good chance that you do not understand what's going on with the data set, and will want to spend some time exploring it first. Statisticians and machine learning people refer to this as exploratory data analysis. And it's an important part to getting comfortable and familiar with the data. Somebody that's involved has to be a domain expert. It's very unlikely and unrealistic to expect at this point that you could just take some arbitrary data, shove it into a generic algorithm, and get any kind of meaningful insight without having some capacity to understand what it's telling you. So we're generally going to try to understand the domain, figure out the plan of approach, understand what is the goal. Are we trying to build some kind of system that's going to make a numerical prediction, or are we building a system that's going to try to classify individual accounts, results, loan applications into a category? And so we generally refer to these as regression or classification problems. We're going to use a technique called supervised learning, where we provide the learning algorithms both the inputs and the outputs, and in the process, it's able to find through the various analytical techniques that the algorithms use, what kind of connection is there between the inputs and the outputs. And from there,
Brian, I'm sorry to stop you, but I saw that we have some questions from attendees not able to find the file. So if you could just share where they can find it, it will be great.
Yep. Okay.
Thank you. Sorry for that.
That's okay. I'm trying to deal with this small screen here, so give me 1 second. All right, so if you go to github.com, Microsoft reactors, oops, typos, all right. You can check out this entire branch. And so this has several of the online events and workshops and various other things. Once you check that out, if you look under the workshop resources, and then look under data science and machine learning, and look under data science 1, the loan project is there. So go to GitHub, check that out. And once you have that, open up in VS Code the directory. So you can just say open and navigate down to that. So in this case, I'm opening up the loan project directory, and it'll do some processing, but eventually it should kick in. You'll need to have the Python 3.8.5 extension installed, but that's as easy as just going to extensions and installing the Python one. So that will give you the ability to edit and debug Python code within Jupyter Notebooks in the browser. So is that okay? Does that answer the questions? Please let me know if anyone's still having issues with it. Okay, so we have these various controls up here, and this allows you to say run all of the cells, or run the cells up to a point, or to refresh, to stop, to clear the cells. So after the overall introduction in the documentation, then we're going to want to start to execute some code. Now, the libraries that are commonly used in Python for machine learning can be anything from TensorFlow, some of the cognitive toolkit stuff, PyTorch. So those are sort of big heavyweight frameworks, but there's also a great sort of lighter weight set of libraries that are not necessarily things that you would run in production, but are very useful for individual data scientists or machine learners, machine learning experts to explore on their own computers and generate models that way. So we're going to use the Numpy library, which is a framework that makes numerics in Python much faster. Normally, Python is, as a dynamic programming language, has a lot of overhead in how it stores numbers and collections of numbers. So it's just not very well suited for numerical calculations when that's the case. But Numpy changes that. So then we're going to use matplotlib, which is a visualization library. That should be matplotlib, not mathplotlib. And then pandas. Can you mute, please? Temporarily. Pandas is a library for manipulating the data. So you can think of it as like almost a programmatic spreadsheet. Allows you to select columns and rows and do some calculations on it. So these are the three main libraries that we're going to be using today. And to make them available to the Jupyter Notebook runtime, we have to import pandas, NumPy, and matplotlib. It's a convenience and a convention to import them with these aliases, just so it's easier to refer to them. But basically, we're just making the functionality available to us in our runtime environment. Because Jupyter Notebooks executes the Python code in an offline process and provides the results back, we generally have to tell it to inline visualization. So when we generate plots, we want to see it in the body of the response. So this %matplotlib inline is just a directive to tell it to show the diagrams here. And then finally, we're going to load in this data set. So we have a comma-separated variable data set in the data directory, under this directory where we've checked things out. So there's functionality in there called read CSV, and that allows us to read it into what's called a data frame. So this is a pandas functionality to read in a CSV file, and then it's available for us to explore. Now, the first thing that you want to know is how to figure out how to get help. And one of the things that you can do is to take the name of a function and end it with a question mark. And if you execute that cell, notice it shows you the signature, it shows you the default values. So most Python frameworks have default values for everything. So you only have to override anything that you want to change. A common thing with this file is if you have maybe a non-comma separated file, but maybe a tab separated file, you would override the separator character from being a comma to being a tab. And that way you could use the same function to read in that kind of data. All right, so once you have the data frame in, you're going to want to explore it. And one of the easiest things you can do is to call the head function on it, which by default is going to show you the first couple of rows. And this is just a good way of getting comfortable and familiar with the layout of the data. So you can see all the features that we talked about, the ID, gender, number of dependents, etc., is available. If you give the head function an argument like 10, you'll notice that you can see the first 10 rows. So by default, it shows you the first 5 rows, but if you give it an argument, it'll show you that many rows. There's also a tail function if you want to look at the last several rows. So we can see that we have 614 rows total, and the last ones based on the default sorting is the loan ID. So this gives us a sense of the size, the shape of the data, the columns that are there. But we also want to know a little bit about the statistical distribution. So again, this isn't a statistics class, but the kinds of things that you want to look for are whether the data looks the way that you expect it to. There's a very common problem where if you have some kind of bias in how you collect the data, then the analytics that it produces are unlikely to give you much useful value. Frequently with elections and things like that. As an example, if you only end up polling people who have landlines, that's going to skew to be an older generation because a lot of younger people just don't have landlines anymore. They just have cell phones. And so the problem is the data that you're collecting doesn't actually look like the population that you're trying to learn about. Therefore, whatever analytics or patterns you find are not going to be reflective of reality, and you'll draw the wrong conclusions. So one of the things that we can do is to look at the statistical distributions, and the describe function gives us the ability to do that for numerical features. So of the numerical features that we have, applicant income, co-applicant income, loan amount, loan term amount, and credit history, which isn't really a numerical term. It's encoded as a dummy variable that just indicates whether the credit history was there or not, or matched the criteria or not. So you can see we have 614 rows of applicant information and co-applicant information, but only 592 rows of loan amounts. So for roughly 22 of the rows that we have some missing values here. We've got about 14 missing values here, and clearly several. We only have suitable credit histories for 564 of the loans. So obviously we've got some missing data, and that's going to have impact on our ability to do analytics as well, because again, we're trying to find evidence in the data that we have, and if we're missing important pieces, that can only mess up our analytics. The other statistics that the describe function gives us tells us like the average value for each of the features. So we see that the average income is 5,403, and if we go back up and check our data dictionary, we see that the applicant income is not listed, but my guess is it's probably in either thousands of dollars or $10,000, tens of thousands of dollars. It's not clear here. We see that the average loan amount is for 146,000. That is expressed in the data dictionary in thousands, and the average loan term is for some number of excuse me, months. So we can see the average value, the standard deviation. That's a measure of how much variation there is in the data set. And if there isn't a lot of variation, then the numbers will be very similar. If there's quite a lot of variation, then some numbers will be much lower, some numbers will be much higher. And that's the kind of thing that we're trying to figure out here as well. Because if the data is completely skewed in the sense that most of the data looks one way, but outliers, we call them, are too high or too low, that's going to impact the quality of the results as well. We see that the minimum value is 150 and the maximum value is 81,000. So that gives us a sense of the range of values. And then these three represent what are called percentiles. And they tell us that 25% of the data set has a value of 2,877 or below. 50% of the data has 3,812 or below, and 75% has 5,795 or below. But if you look at the gap between the 75th percentile and the maximum value, which represents the 100th percentile, we see that there's quite a big difference between where most of the data is and where some of the people who are coming in and acquiring loans are financially. So we've read the data in, we have the ability to explore it through the head function, we've got the ability to describe it from a statistics perspective. Pandas very conveniently does this per feature and gives us the ability to get a sense of the shape of the data before we do anything else. There's another function called info on the data frame that tells us not only like how much memory is being used, but the types of each of the columns. So these are called object columns because they are categorical data, or they are numerical columns if they're numerical data. But it also gives us a pretty good summary also of what's missing. So we see, again, 13, 2 or 3, 15, 40 or so, or 30 or so missing rows. So that's the first thing that we're going to try to do, is we're going to try to come in and fix some of the results after we drop the columns that we no longer want. So if we go back and look at our head function, which I removed, sorry, I'll do it here quickly. The data still has the various elements in it, like gender and married. So let's go ahead and drop those columns. We're going to pass in the array of the column names that we do not want to have, and then that's going to produce a version that doesn't have that data in it. So notice, however, that the original data frame still has them in them. So we're going to instead have to capture the result of dropping the columns. So I'll say data frame equals data frame drop column. And now if I look at the result, those are no longer stored in the variable. So this drop just returns a view with those columns missing. Oftentimes you'll want to drop some of the columns and explore the data, but still have your original data set there. So oftentimes, rather than assigning the value directly over it, you'll assign a new variable that says, without gender and married or something like that, with dropped values. But for our purposes, we're not going to use those, so it's fine to overwrite the data frame. Now, once you do that, once you manipulate the data frame a little bit, you may want to save it out. So there's a function called toCSV that will give you the cleaned up version. So this is going to save it out as a loan prediction training data with no gender or married status. So that way, if you want to come back to it, you can come back to it in the future. All right, so in addition to the numerical data, we also have categorical data, and that's not usefully summarized by statistics. So there's a useful function called a value counts, and if we apply it to a particular column, it will go through and count up all the individual values and keep track of how many there are for each value. So in the self-employed column, we see that there are 500 non-self-employed loan applicants and 82 self-employed applicants. So obviously, if being self-employed means maybe life is not as steady or predictable, maybe that factors into the loan. The property area section, we see that most of the loans are in urban or semi-urban areas. So, maybe talking to commercial real estate or people buying houses or apartments or condominiums in urban areas is the more likely set, which either could be the reality of how the loans are being distributed, or perhaps we have a skew in our data set towards more urban areas. Just, we reach out to people, and people who respond may come from a particular area. So these are the sorts of things you're going to want to sort out and get comfortable with, and work with a loan domain expert to determine whether there's some kind of issue with the data that you've collected. Obviously, your education level will correlate to the kinds of jobs that you can get, which then will correlate with income. So if we look at the in the income levels, we can tell whether how many people are graduates or not graduates from college, which will give us some insight into the outcomes as well. So we've got various tools, statistical tools, summary tools. These value counts help us deal with the categorical data. This is all just about familiarizing ourselves with the data sets. But then we're going to want to look at the shape of the data a little bit more. We've hinted at this in the numerical summaries, but we're generally fairly visual creatures, so things jump out to us a little bit more easily when we can see it visually. Now, the good news is, directly off of the series result that we get by pulling out this column, we can call the hist function on it, which will generate a histogram with 50 bins. And the bins are broken up into, we have a continuous range of values, and then the values drop into the individual elements. And so notice, just visually looking at the distribution, we saw what we saw numerically, which was that most of the loan applicants are down here, and the people who have much higher incomes go all the way up here. There's just not a whole lot of them, which is, our understanding of the distribution of wealth in general, right? Most people aren't super wealthy, and people who aren't super wealthy need loans to purchase things. And so that seems to be suggested visually in what we're dealing with. But it's nice that this can be all done in line, one line of code, in a language like Java or some other language. This might be several lines of code to set up the graph, but these are nice, well-designed APIs for the most part. So histograms are one way of looking at this. A box plot is another way of looking at the distributions. So notice we're specifying which columns we want to pull out of the data frame. And this particular one is then, again, the applicant's income. The lower bar here represents the minimum value. So we obviously we're at 0. The upper bar represents a percentage of the overall value. In this case, probably around the 75th percentile or somewhere around there. And then this box here that's kind of flattened shows you what's called the interquartile range. It's the middle 50%. And it's a way of excluding the outliers and looking that, most of the data falls in this middle range here. And obviously that's a very narrow range. So we can see the long tail impact of the outliers, which are going to skew the results a little bit. So that's the kind of thing we're going to want to clean up and when we go through this process. But it's also perhaps interesting to explore income based on other categorical factors. One of them that we might want to consider is education. So we can rerun the box plot on income, but also ask it to separate it out based on education level. And we see that the upper range of the non-graduates is much narrower than the upper range of the graduates. And again, this is a consequence of the opportunities that are given or are available for people with specific skill sets. So, these could be bankers or, investment people who have very specialized skills that are well rewarded by certain industries. So there's lots of reasons why this could be the case, but we see that there's less variation amongst the non-college graduates versus the graduates. We could break this down based on whether they're self-employed or not, right? So this is the kind of thing where after this session, I encourage you to play around and try out some of these other comparisons and just see what other additional insights you get in the process as well. All right. Again, please do call out if there are any questions. I can't see them, but I also am trying to get caught up because of the delays, so I'm moving fairly quickly. But happy to try to help answer any questions if there are any. We might want to look at the distribution of the loan amounts. So again, we're selecting from the data frame the loan amount column, generating a histogram from it. And this shows us that there's not quite as much of a long tail of outliers, but still, we can see that some of the loans are a much higher level than others. Obviously, that's going to correlate with the people who have much higher incomes. But the majority of the loans are in the 100,000 range, because again, these are expressed in terms of thousands based on the data dictionary. The box plot of the loan amounts gives us some insight about the distribution there. And again, most of the loans are falling in this middle 50%, which you see correlating with the large number of counts in the histogram up here. So in this way, visualization helps you in your data exploration to understand trends in the data. And these are just tools for helping you understand that. And then the box plot of loan amount based on education. Notice that seems to look quite a bit like the income level. So it seems unsurprisingly, we give graduates a wider range of loans, and those outliers of those wider range of loans very much corresponds to the outliers in the income in the graduates. And we see that, the loan sizes for non-graduates is capped at a certain level based on their income level and whatnot. So it's unsurprising that we would see a similar structure in terms of the outcome of the loans based on the correlation with the inputs that and the importance of income to a loan decision process. But there could be other considerations. Somebody may not make a lot of money, but they may have some family money, or they may have saved up a bunch of money over time, and then therefore would be a better loan applicant as well. All right, and then finally, if you want to compare the loan amounts with whether people are self-employed or not, it seems like obviously there's some difference, but we see a wider range of values in the middle 50% in the interquartile range for the self-employed people. But the distribution isn't as strong as it is, or out skewed as some of the other ones are. So again, we've got some places in here for you to think about these explorations and give you some space to try out some of the other histograms and box plots of the features that we have. So this is helping us get some sense of the distribution, but now before we do any actual calculations, we're going to have to deal with the categorical data and somehow turn them into numbers. So one of the things that we can do is we can look at the credit history, which again indicates whether we have a matching credit history for the various candidates. So we're going to do a value counts in ascending order. That's just going to make sure that we have the zeros first and then the ones. But this is going to generate a summary. We call it a frequency table on the credit history. And then we're going to generate a pivot table that's going to allow us to explore in a little bit more detail the interrelationship between the status of loans and the credit history. But because this is categorical data, and we're going to try to generate some numerics from it, notice we can pass in a lambda function. That's just a way of specifying kind of a detached bit of computation. So in this case, we're going to map the yeses to ones and the nos to zeros, and that way we can do some summary statistics on those as well. So we're going to print out the results once we have them, and we see that of the applications that we had, 475 of them had matching credit histories that were useful, 89 did not. So again, somebody who doesn't necessarily have established credit isn't going to necessarily be excluded, but we see that more people get loans if they have credit history. And so that's one of those, how can I get a credit history if you won't give me a loan to get started situations. But presumably, the people that we have loans for and whether they were given a loan, this can be indicated here. So notice of the people who did not have who did have a credit history, 80% of them roughly got loans. For those that did not have credit history, only about 8% of them did. So for whatever reason, the applicants were deemed too risky at that moment in time, and maybe they'd have to go save some more money, or maybe get a credit card and use it reasonably for a while to establish a bit more credit history, and maybe that would change the impact of the loan after the fact. So this kind of analysis of the categorical data is useful as a means of getting a sense of the summary of the distributions. But then you may want to ask, how do you figure out the average value for the loan status column, in the sense of on average who got loans and who didn't? So we can do something like, let's take the credit history, or the loan status. This first step here will return the column values. So we just see that we have the yeses and the nos. Then I can turn that into a value counts, which will then summarize those. Sorry, there's a lot going on this machine. It's just not the one I was planning on demonstrating this on. So that'll come back in a second, and it'll give us the summary of the data. And from there, we could divide it by the number of rows, which we could calculate by one. But we also remember that there were 614 rows. So if we just divide by that, that will be applied, and we see that roughly 70% of the things that were given 70% of the applicants were given loans. So that's mixing everybody all together and is an overall sense of the acceptance rate. You know, this is independent of their qualifications or anything like that. We're just saying in general of the applicants that we have, how many of them were given loans. These sorts of things are very useful to plot. So we can also look at Matplotlib, generate a couple of figures, and we will configure the diagrams. You can set the labels for the axes. The X label will represent credit history. The Y label will indicate the number of applicants. And we're going to tell it to be a bar chart. And so then we're going to map credit history and probability of approval. So this is based on the data that we calculated a couple of rows up. And we can see that, you know, the majority of the people who applied did have credit history, and most of the loans that were given were done for people with a credit history. So again, we can sort of correlate independent of the individual values, just overall, what percentage, how important was credit history to the decision, and unsurprisingly, it's a very important part of the result. So again, as an exercise, you can go back and try changing out some of the other things to see how important being self-employed or what the property area, you know, urban versus rural, and those implications. Obviously, we dropped married, so that shouldn't be there. But the other features might be useful, and you could measure just independently from a percentage perspective, how important were those to the qualities. All right, it's also useful to compare things. So let's compare what we're going to generate. It's called a crosstab. If you're not familiar with that, don't forget your ability to look up help with the question mark. Notice Visual Code also allows you to hover over it. So it says this will compute a simple cross tabulation of 2 or more factors. And so it's going to generate a frequency table from that result. So we're going to do a crosstab of credit history versus loan status, and then plot the results on a bar. And it's easy to see the difference. So do you have a credit history? No. Okay, well, how many loans do we have? How many loans were not applied? So the red shows, you know, you did not get a loan with no credit history. Here we have the reds. You did have a credit history, but you still didn't get a loan, versus the ones that did. So obviously, this is just another way of presenting the same information. But this is useful for telling other people about your decision process as well. The analytical visualizations that you use to gain insight in the data may be the wrong things to present to business stakeholders. And so that's the kind of thing that you're going to want to have to decide who is the audience for the story that you're telling. And this is a very easy thing to see how important credit history is to the success of a loan. So we could also go through and check out other ones as well. So this is now, we've gone through the process of collecting the data, exploring it, visualizing it. You'll have gone through to try to find where there is correlation between the fields and the outcomes. And that gives you a sense of which features do you want to try to build your results on. And just to try to wrap up relatively quickly, and again, I'm sorry about the delay. We're going to now clean up the data. And one of the things that we're going to do is to apply a lambda function again. So this is just a function that's going to be applied to each of the rows. And so in this case, I want to count up how many rows have null values. So for every row that's, or every field that's there, we can go through and figure out. Well, we've got a loan ID for everybody. That's not surprising. We've got education information for everybody, and applicant income So we're not missing any values for there. We don't know whether some of the rows have dependents. We don't know whether some of them are self-employed. So again, with those missing values, the math won't make sense unless we come up with some kind of meaningful solution. And this is where data scientists can kind of cause problems if they don't understand the data. If we just zeroed everything out, think about what that would do. That would pull all the average values down and affect the quality of the results. So sometimes it's okay to zero things out, but other times you're going to want to fill in missing values with like the average value for that field for everything else. So again, imagine you're trying to build a basketball team and height is important to whether somebody's a good basketball player. You might fill in missing values for height based on the average values of the rest of the results. So if the average player is 5'10" in like a high school team or something, then that may be a reasonable value to fit in. It's certainly not going to impact the analytics in the same way that setting it to 0 would. So this next section is just going through and figuring out how to fill in some of these missing values. We're going to fill in the missing loan amounts with the average values of the other loan amounts. So again, this is probably not, super accurate, but it's not going to adversely affect us because the average value of everything else will continue to be the same average value. We're just assigning it to the rows that we have missing values. And so this is a lot of functionalities to do in one step. We're saying take the rows that have non-missing values and fill them in with the average of the other ones. The in place means do it directly on this. Otherwise, this would generate a view of the data and our subsequent data frames will not reflect the fact that we filled in the results. But because we do it in place, it goes ahead and modifies the data frame. So if we do that, then we can apply the lambda function, and for loan amounts, we see that we're no longer missing any results. So now if we look at the average results, or the value counts, we can see the distributions, and most of the loan amounts were in the 146,000 range, which looks about like what we would expect from the data we saw earlier. All right, so then we want to fill in some values for the self-employed column, but that may or may not be as easy to consider. Like we don't know necessarily what the distribution of the results is yet. So we can see for education, the difference between loan amounts for graduates versus non-graduates, and the self-employed people, we see the loan amounts for self-employed and non-self-employed people. The reason that's important is there's obviously a distribution of values, and if we say that the average, loan value includes all of this data, well, for non-graduates, that's not going to make a whole lot of sense. So what we're trying to do is to say, within sub-view of the data, can we get a better guess of what the value should be for the people who have those particular categories? So this next step here is going to tell us roughly what the distribution is. Most of the people are not self-employed. The percentage of no's is 85.9%. So that's roughly 86% of the population is not self-employed.
Brian, we just have a request if you could please zoom in so they can view the code better.
I'm not sure how to do that, and we're running out of time, but I will try.
Okay, sure.
Hopefully that's a little bit better right there. Again, you have access to this. The video will be made available. You can go back and watch it and connect it to the things if it wasn't easy to read earlier. I apologize about that. And is it okay for me to go just a little bit long?
Yes, that's fine.
Okay, then I'll finish up, but I'll try to do so and still leave some time for some questions. So we see that about 86% of the applicants are not self-employed. So given that that's the majority value, it's probably okay to fill in no for the missing values for that. Again, this is the kind of thing where you're going to want to talk to a domain expert. Is this an okay thing to do? Is this an okay assumption? Because you are actually transforming the data in this process, and that may skew the results. So these are all showing you mechanisms that you can do, but whether it makes sense to do so or not should be verified by somebody who understands the domain very well. But as you can see, we're filling in the missing results. We're down to a couple of here for dependents and a couple of here for the loan terms. And so we can create a pivot table of self-employed and graduates. And so this basically tells us, of the various loan amounts, how does it break down? So self-employed people who were graduates, the median loan, which represents the middle 50 percentile, is 131,000. For graduates, it's 115,000. For self-employed graduates, it's 152. For self-employed non-graduates, it's 130. So this gives us a structure to the average values at the intersection of these various fields. And then this very cool function is going to basically generate a table of the relationships between those distributions, and then we're going to fill in the missing results by pulling those together in place through that function. So it's a lot going on in one line of code, but when we look at the results, we now should have filled in the loan amounts and status and the other things. So we've got a couple more that we're gonna address, and then we'll be ready to do our training. Because of the variation in the loan amounts, so some are smaller and some are much larger, oftentimes the feature selection process gives us the ability to obviously see how important the loan amount is to whether it was granted or not. But that kind of variation, again, so few of the results have this very high amount. So sometimes you want to do what's called feature engineering or feature scaling to make that be less impactful. And so one of the transformations that we can do is to take the logarithm of the loan amounts, which will sometimes turn it into more of a linear relationship in the results, or at least reduce the impact of the skew. So notice if I take the logarithm of the loan amounts, the distribution is over a smaller range and it doesn't seem quite as skewed. So obviously these are the much larger loans up here in the hundreds of thousands versus the tens of thousands down here, or up into millions, whatever that would be. So this is transforming the data, but hopefully in a way that's going to positively impact our capacity to learn from it, because the underlying skew of the data won't be quite as negatively impactful. All right, so the other thing that we want to do is to realize that the total income is the applicant's income plus the co-applicant's income. So we're going to generate a new column. One of the things here we did was we created a new column by applying a log transformation of the individual values. So for every loan amount value that we have, we're going to take the log of that and assign it to a new column. So this is now a new column in our data frame. We're going to do the same thing here for total income. We're going to create a new column that is the sum of the applicant's income and the co-applicant's income, and that's going to give us a distribution as well, which here we'll do, sorry. total amount or total income log. So again, we've got the majority of the total income is now in this range, but it's when two people are working together to apply for a loan. That's the total income that we're going to consider. So that should be the feature that we're trying to look at. I mean, it doesn't really matter if one person contributes 80 and one person contributes 20, or one person contributes 100. It's the total between the two that's going to be important. So this looks like a reasonable distribution, and we may want to then do some more cleanup of the data. So the process is to collect the data, exploratory data analysis, and then the ability to perhaps do some transformation with the data. Now we're ready to build our model, and we have a new library we're going to use called scikit-learn. So far we've used NumPy and matplotlib and data pandas. Scikit-learn is the thing that gives us the algorithms for doing the machine learning. So if we have missing results, we can put them in place. I'm going to pull out those because those shouldn't be there. So we're going to we're going to say for everything else, we have a handful of missing results in the results, but we're going to fill them in with the mode. So the mean is the average value, the median is the middle value, and the mode is the most common value. So for dependence, we're going to say not what's the average value, but what's the most common value for dependence. Any missing results we're going to fill in for there. Same thing for the loan term, same thing for the credit history. These may or may not be the appropriate things to do, but they seem like reasonable approaches as well. Then we're going to encode the individual categorical results with what's called a label encoder, and you'll see the impact of that. So let's we now have encoded things that up until now, like education, had been an object. It is now encoded as a numeric value for each of the values. So self-employed was yes or no. Now it's going to be a 0 or 1. So we're taking each of the results and exploring that. We can see the impact if we look at the head of our data frame again. Notice education is now 0 or 1, self-employed is 0 or 1. And because the model that we're going to build now initially is called a logistic regression, it's an unfortunate name because it's really a classifier. It's going to use the mathematical combination of these features in a predictive way. So if we say number of dependents is 1, then mathematically there may be a coefficient associated with dependents. So people who don't have dependents will zero out that coefficient, but people who do have a dependent will be impacted by that coefficient. Same thing for education. If being a graduate or not a graduate is impactful in the predictive power, if you're not a graduate, it'll zero it out. If you are a graduate, maybe it gives you a boost. So each one of these features is now a numerical element, and so we can build up our model. So we're going to use a logistic regression model. We're going to also pull in another one to do some other comparisons. And we're going to use this metrics library to score the results. So we're defining a function. We are going to take our predictors and our outcome. We're going to do the machine learning training right there. That's where we fit our inputs to our outputs. Again, our output here is whether the loan succeeded or not. We're going to then take our predictors and make predictions and compare the predictions to the actual results. So normally we would split this up into training and test data, but for this particular example, we're just going to see how well during the training process did the results actually do. And then we're going to explore some options. So the logistical regression model is a technique. It's based on a transformation function called a sigmoid function. And in essence, you're trying to have an infinite range of inputs and map them down to a series of single outputs. So in this case, we want to know whether you'd get the loan or not. So that would be mapping it to a 0 or a 1. So we're going to start with the outcome variable, loan status. That's the thing we're going to try to predict. The model is going to be a logistic regression model, and the input predictor is just simply going to be credit history. So we're not basing it on all of our data, we're just basing it on just the credit history and building the model from it. And now we can see that this generated an 80.95% accuracy. So what this tells us is, of the loans that were given, roughly 80% of the predictive power can come from credit history, right? If you have a credit history that seems to correlate very highly with the outcome, we saw that reflected in the data. We saw that in the distribution, we saw that in the visualization, but we can then try to improve our results by looking at other features. So let's look at applicant income. So in this case, we can compare applicant income. Oops. I'm not going to go down there. I'm not going to try to bug it given our short amount of time, but you could go through and compare other sorts of features. It could be like I could have maybe the wrong number or something in there. Sorry. It's also very early in the morning here. So what this allows you to go through is to look at the various features for a particular model, build a simple predictor, and the idea is then for future applicants, if they were filling out a form, then you could give them a hint of, well, based on historical distribution of success or failure in the application process, it seems unlikely that you would get a loan based on what you've told us. So you can be helpful to people, like not make them actually go through the process of being rejected, but give them a sense of the likelihood based on previous loans. And that may then give them some things to go work on, like go establish a credit history, save up some money for a down payment, find a co-applicant. Right? You could come back and give them specific advice based on the results that you saw. Now, a logistic regression is just one type of classification. We could come through and do some other results using other algorithms. So for example, let's try gender or remove gender and married there. We'll try credit history and education and compare the results and see that gives us roughly the same impact. So a decision tree isn't able to do much better with the same basic information, and to the extent that education is correlated with income, and income may be correlated with the presence of a credit history, it doesn't seem like there's a whole lot of extra information that's being given to us. But we could go through and try to build a more complex model using other features like a random forest classifier and looking at dependence in education and whether people are self-employed and which types of property that are there. And notice this has a much higher accuracy rate. And that may seem, wow, that's much better. But because we're only working with training data and not test data, we don't know whether the random forest classifier is actually learning a better result or if it's just memorizing the details. So we're training it off of this data. this is a more flexible model, so it's able to learn more from the data than a logistic regression one is. But if you have a child who finds the answer sheet in the teacher's desk and memorizes the answers, then he's going to look very good when he takes the test, and the teacher will be surprised, like, wow, you did a great job. But if you ask this child another question that wasn't on the test, you will very quickly realize they don't actually understand what's going on. And that's what we're concerned about when we have overfitting. If the model is too flexible, then it will absorb too much of the information. And that translates to, in essence, just memorizing the details. And so that's usually why we'll have training and test data, because if we do well in training and well in test data, then we're not concerned about overfitting. If you do well in training and don't do well with the test data, then you're probably overfitting and you'll want to tune accordingly. So the goal isn't always to pick the most flexible model or the most powerful model or even the model with the highest prediction value, because ultimately you may need to explain how and why were these decisions made. And these decisions could be based on things that you shouldn't be using, like gender or somebody's marital status or something. Or there could be correlation between the features. So again, this is why we couch machine learning in a data science activity, to keep us honest, to keep us aware of the quality of the results, and try to fit the right problem to the right solution. A model that does well predictively and isn't overfitting could be very useful for some kind of data product like a recommendation system, but a model that does good at prediction that's hard to explain might do poorly in a business context where you need to explain your results. Either it's regulation, or simply the business people aren't going to be motivated by things clustering in high-dimensional vector spaces, right? You need to explain things to them in business terms. So again, I apologize about the late start and the quick trip through this, but I hope we gave you a lot to think about and some things to play around with. The take home here, though, is picking models is one part of the story. Picking features is another part of the story. Matching those features to the outcomes that you're trying to learn is called feature selection. Modifying the features so that they are within a closer value range, that's called feature engineering or feature scaling. And that may amplify the signal that's there in the features that correlate with the output. But even then, you're still going to want to explore the data. You're going to make sure that your collection process is not biasing the data in some way. Because again, if you're only collecting information from wealthy people or only collecting information from people who are less wealthy, that doesn't give you a complete picture of what goes into the loan making process. So you need to make sure that all aspects of this analytical workflow are not introducing problems that affect the quality of the outcomes and the predictions. And if you are not a loan expert, you may not be qualified to evaluate whether these things are done or not. So that's why it's good. We use machine learning to understand domains and make predictions about domains, but we're still going to need domain experts to evaluate the outcomes. So with that, I'll see if there are any questions, but I hope this was interesting and useful.
Thank you, Brian. That was a really interesting presentation. Thank you for the demo and for taking the time, all of you, to join us. We apologize for the delay and for starting late, but hope you could join and stay with us until now. As I mentioned, also the session was recorded, and it will be available on our YouTube channel within a few days. I think we covered some of the questions during the session. The last one that we just received is how do you deal with the unbalanced data? And I will see if we had other questions that we didn't pick up, and I can address them to you.
Sure. Again, there's no right answer all the time, but you'll want to make sure that the unbalanced data isn't unbalanced with respect to the population, but it is also, if there is an imbalance in the data, like we saw with income variation and whatnot, that may be something that you can address with transformations of the data, or you may need to address with different collection processes if somehow there's the imbalance is some kind of inappropriate bias. There are other analytical techniques as well. I'm unfortunately, my headphones are about to run out of juice though, so I don't have a lot of time left before I lose sound. So
I don't see that we have any other questions, so I think we can end the session now. So thank you so much, Brian, for your time, and thank you everyone who joined us. We hope you enjoyed it, and we hope to see you in our next event.
Thank you very much.
Okay, bye-bye.